The topic for today is space requirements and layout. And this material is part of, if you want to follow your syllabus, this material is part of chapter 3 and chapter 9 of your textbook. So the idea, if you first show you the objective. Now we are dealing with objective number 4 in our lecture, which is be able to design layouts incorporating product, process, and personal requirements. And the agenda for today, I'm going to provide a little brief introduction for this topic, and then between today and Wednesday, we're going to talk about these different systems within the facility. First of them is structural system performance, enclosure systems, atmospheric systems, electrical and lighting systems, and life safety systems. All these systems, but today we're going to focus on the first three, structural, enclosure, and atmospheric. So the objective in terms of the learning objective for this lecture is to provide an overview of how the systems elements impact the overall process of facilities planning, provide an understanding of the various systems elements within the facility. Once you start seeing this material, you'll think, oh, well, this is some of the stuff that maybe a civil engineering would do or another type of engineering discipline will take care of. But the idea of this lecture is not taking you to that area. What you want to be prepared, the lecture is not to prepare the facilities planning to design a structure of its heating, ventilation, and air conditioner or other system. What you want to do is to understand what those systems involve. So when you start planning for your facility, you have a good understanding of how those systems will affect your design. Okay? So hopefully that's clear. And that being said, let's provide a brief introduction. And I think we talked about space requirements already a little bit. We did a brief introduction about this topic in one of our lectures. So going back to that, the most difficult determination in facilities planning is the amount of space required in the facility. And when you plan for a facility, there's some uncertainty in terms of what can happen in the future. And some of the things, because uncertainty generally exists concerning the impact of technology, changing product mix, the introduction of new products, for instance, the changing in demand patterns, and the organizational design for the future. So when taking all these things in consideration, then the facilities planner has a difficult task in terms of projecting the true space requirements for the uncertain future. So the idea with this topic is you're going to have to deal with this uncertainty, but also when you're planning your facility, you need to take into account that there are going to be other systems that are going to be occupying space in your facility. So we talk about the best way to start planning for facilities by starting by designing the workspace or the workstations for your workers. Then from them, once you have those space requirements designed for individual workstations, then you can design the department. So the space requirements for each department can be established. And in this picture, we provide an idea of how a department might look like. We have multiple workstations. We have a big machine in this corner. We have all the boards, have some type of office space in this area, and so on. So planning the facility systems is typically not the responsibility of the facilities planner. And when I refer to systems, now I'm talking about the electrical systems, the HVAC systems, and so on. But the responsibility of the facilities planner is specifying what systems are required and integrating those systems into the overall facility. Okay, so you're gonna determine, okay, we're gonna need an HVAC maybe for this space of the facility, or we're gonna need another type of ventilation system for this area, for the warehouse, and so on. The facilities planning must be aware of the cost of constructing, operating, and maintaining a facility. And this is greatly impacted by the type of systems that you're going to have within the facility. And a critical factor affecting the facility flexibility is the facility systems. And when you talk about specifically, let's say, the design of columns for your facility, once those are placed, there's no way that you can move them. So that's why having planned for this very carefully allows you to have more flexibility. A facility plan is not complete until all systems are specified. Something else that's very important is that facility systems have an important impact on employee performance, morale, and safety. So if you go to any facility where if you go to any warehouse within the facility, most of the time warehouses are not they don't have air conditioner, or so they are open spaces most of the time. You get employees not very happy when the heat comes or when the winter comes, because they're going to be dealing with these different temperatures. So that affects the performance, that affects the morale of the employee. Facility systems have an important impact on the fire protection, maintenance, and security of a facility. So planning for these systems is very important. And on the next slide, I'm going to list them again. What are the systems that we're going to be studying that affect the design of your facility? And what are these systems that are required also to have a final plan for your facility when you are trying to design a new facility? So these systems are structural systems, atmospheric systems, enclosure systems, lighting, and electrical systems, and life safety systems. And when we are talking about facility, you know, most of the time we're talking about very large structures. So here I'm presenting basically the skeleton of such type of facility or structure. So you're going to have different materials coming together to hold this big roof and the walls and so on. So you're going to talk about these things in this lecture. So let's talk about the structural system performance. And specifically, column spacing. So one more time, when you design a facility, you want to know where the columns are placed, because you know when these are placed, you know you're not going to have any opportunity to change the location of those structures in the future. So the most common structural types of our industrial facilities are the steel skeleton frame or reinforced concrete skeleton frame. So most of the time, these are the two type of structures that you're going to see. The column configuration will impact the layout that you're going to be providing to your facility, and the layout will affect the structural design. So if you have an idea of the type of departments that you're going to need for your facility, and the location of your machines, the location of your warehouse, and so on, then you might have an input, or you should have an input in terms of designing this structure, because you know you're going to have to transport some of these goods within the facility. You're going to have employees, so you need to look for their safety and so on. So the facilities planner must insist that the structural grid spacings optimize the function of the facility. So for example, in a warehouse, the column spacing should be dictated by the rack dimensions and the access aisles between the racks. So you want to have enough space, so if you're going to be moving forklifts within your warehouse, you want to have enough space for those forklifts to move, and also to pick up the goods and move them to other areas of the facility. A common error in designing warehousing facilities is using building cost as the criteria to define column spacing and determine the grid configuration. So in other words, this is not where you want to save money. Okay, remember, this is going to be something that is going to be fixed. So once you determine the location of these columns, you are not going to be able to move them. So you want to plan very carefully, and you want to make sure that you're using the right materials and the right type of column. There's different type of columns. Here I'm listing two of them: the heavy wall round or the square tubular columns. Those are the ones that you want to have in your warehouse. There's other type of columns, I don't know if you have seen them, that have like an H shape. So those are not very good. These two type of columns are a little more expensive, but provide a much better facility in the long run. Here are some of the reasons why. Eliminate rodent and vermin nesting places, ensure easy maintenance and cleanness so you don't have stuff accumulated inside the columns, provide the ability to place downspouts within the columns, and minimize the effects of denting on column strength. Eliminate the corners that can pull packages from the pallets when work trucks are moving throughout the facility. So one more time, here's not where you want to save money. You want to make sure that you're using the right type of column, specifically if you're designing a warehouse. Now let's move to another type of system that is called Enclosure Systems. And now we're going to deal with the entrance of the facility and how that impacts the status of the facility. So the enclosure systems provide a barrier against the effects of extreme cold or heat, lateral forces such as the wind, water, and other type of undesirable entries like insects or subjects that are not related to the facility, so humans. And these are very easy to identify. Most of the time we have three types of elements: the floor, the walls, and the roof. So those are the elements that are going to be enclosed in your facility. All three elements are intended to provide the facility with a specified comfort level, often impacted by the thermal performance and of the building enclosure. So most of the time you want to keep this equation in mind. The building enclosure plus the service input is equal to the comfort level that you're gonna or your employees are gonna experience in your facility. So in terms of thermal performance, the thermal performance is usually required to rectify the heat transmission between the inside and the outside of the facility. So here the climate is the major determinant, and one of the major problems in thermal performance is how to make effective use of the solar gain. So most often you're seeing now facilities looking at how to use solar energy to power some of their areas by use of solar panels or reflecting that energy out of the facility to keep the temperatures down. So that's the type of thing that we are looking at here right now. Solar transmission if it is effectively controlled, can significantly reduce the building's dependence on artificial atmospheric systems. So again, for this type of systems, you're going to have to be very aware of what's the type of weather that you're going to get in the location that you are working on, and so on. So we have three pictures here just to give you an idea how the solar energy can impact your facility design. So if you only have a roof, single glaze type of roof that is clear, then 90% of the incident solar rays are transmitted due to the poor absorption of the reflection quantities of the single glaze element. But then if you add another element to that design, let's put a heat absorbing roof cover, then instead of having that 90% going inside your facility, now you're going to have half of that inside your facility. So that give you, you can lower the heat or the hot weather inside your facility. So a double pane configuration with a heat absorbing element reduces the amount of transmission by half. But if instead of using a heat absorbing type of coat, you use a reflective type of roof, which obviously is going to be more expensive, the solar gain can be reduced additionally from 90 to 25%, so an additional 20%, by using a reflective glass member in the roof of your facility. So all these things are important design concepts that you can take into account. And again, it's going to depend on how much, what's the temperature that you're going to require within your facility, and how much you're going to save in terms of adding these elements in your facility. So barrier performance, the material selected, metal, plastic, or masonry cladding, should be more impervious to penetration, and thermal performance coupled with water exclusion forms the backbone of most enclosure systems. You don't want to have any filtration within your roof. You want to try to keep the weather or the temperature within your facility in a comfortable level. So there are two areas that you need to consider. There's the above the ground and the below the ground. So looking at the first one, above the ground, facilities planners must be aware of the problems that a poorly designed roof can cause. Again, water filtration, the solar gain, and so on. And the primary performance need of the roof is the water exclusion. So if you let water go into your facility, then you have the problem of creating mold or maybe affecting your production or your products. So by vapor migration, good insulation, and water barrier and removal are essential to an effective roofing system. And again, once there's other type of ideas that you can take into account now in these times for designing your roof. One of those ideas is what is called a green roof. And on those type of roof, you're going to have some type of vegetation in your roof. So that would give you some barrier for your facility. And some of the advantages is reducing heating and cooling requirements. protecting roof components from UV rays, and dealing with wind and temperature fluctuations. And finally, reducing the site's impervious surface area, meaning that you need to have some, when you're designing your facility, you need to have some percentage of your area that is for vegetation. So this will allow you to have more space for other things because you are already providing that area in your roof. So in terms of ground and below ground, the ground and below ground condition for industrial facility is typically a concrete slab sitting directly on the ground. So we have one picture here. This most likely for a house, small type of slab. But that's the same concept. You're going to have a concrete slab that's going to be holding most of your facility. And the primary concern with ground conditions are the water penetration and the vapor migration. So you want to make sure that this concrete slab for your facility is not allowing any type of water penetration, and also have some type of migration for the vapor. In terms of the floor performance, in most manufacturing systems and warehouse facilities, the floor is second only to the roof in terms of performance requirements. Over the time, these concrete slab floors tend to crack or dust and generally deteriorate. So you want to make sure that you provide a good maintenance for the floor. Again, this also relates to the safety of your employees. So some tips for preventing some of these conditions are as follows: the steel fiber, which can be mixed with the concrete. This will not prevent the crack, but will reduce the width of the crack once they occur. So they will not go above 1/8 of an inch. Synthetic fibers, this also mixed into the concrete to reduce segregation of the concrete mixtures as it dries, and therefore help to reduce the formation of the cracks. And this is something that you can see also in houses in this area. If you go to the garage, you'll see that most of the houses in this area will have some very small cracks. That also depends on the type of land that you're dealing with. But that's something that's going to happen for sure, because these terrains are going to move. So atmospheric systems. Now we're going to deal with other type of system here. We're going to talk about HVAC systems and how to plan for those type of systems within a facility. So the atmospheric systems provide for the health and comfort of the occupants, and for the needs of the building equipment and machinery. Um, Maintaining the work environment, there's some codes that you need to follow. So codes require only minimum temperatures or indoor temperatures in winter and market standards for different building types provide more precise responses involving cooling and humidification. So one example, and I'm very familiar with this type of designs, is for healthcare facilities. Humidity is held close to 50%. And this is just to try to find the optimum level of humidity to inhibit the growth of viruses and bacteria. So that's one type of requirement. A more significant problem is the introduction of inorganic chemical pollutants into the building from sources in the building. Major air quality problem in most buildings is the buildup of odor and airborne particulate matter. And the rate of dilution is what we use to measure these quality problems, and this is expressed in as a feet cube divided by minutes times feet square of flow area. So this is the type of measurement that is used to measure the air quality within your facility. One way that we can see to eliminate unwanted substances is to dilute them by both mixing stale air that is in the building and by adding fresh outdoor air. So this is also important, specifically when you have very sealed facilities. You want to keep a source of fresh outdoor air coming into your facility so you can eliminate those problems with the air quality. So this air exchange or dilution rate is typically expressed in air changes per hour, and it is stipulated by local code requirements. As it pertains to the building use. So here are some of the examples for some of the type of buildings, including the residence, and some of the rooms for the house. So we have some type of exhaust systems for those areas, including the restrooms and the kitchen. So those where you see those fans most of the time. That's the reason why. For office and commercial, you also have some minimum requirements that you need to satisfy: schools, public assembly, hospitals, and so on. So the equipment to bring in fresh air and remove stale air is primarily a consideration in planning a facility. And in order to plan for these systems, most of the time this is going to occupy some big area of your facility. We need to plan for the space requirements for such type of system. So equipment rooms, this is the space requirement that you're gonna need to place the systems, and there's some space requirements in governed by the size of the equipment room. And here's some percentages in terms of the type of building that you're trying to address. So for residential use, area of the equipment room is around 2%. But for example, for a lab, that could be between 25, almost half of the facility dedicated for these equipments. So as the air change rate increases, the handling equipment area also increases. So there's a straight line relationship between these two. So if you need more, you need to take all these others outside your facility, you're going to require more equipment to do that. So again, the important thing about these systems is that it's going to occupy some area of your facility, so you need to be sure where to place those equipment and also be aware of the area that it's going to occupy. Some other things to take into account is the duct sizes. So duct sizes can be estimated from air quantities and air speeds in ducts. So main duct, 1,800 feet per minute, branch ducts between 900 and 1,100 feet per minute. And the louver size, these areas are also estimated from air quantities and air speeds. So we have also some recommended measurements for these two types of louvers. So for the purpose of the exam, you don't have to memorize all these numbers. Again, once you finish your degree, there's no way that you're going to memorize all these specifics, design, measurements, but it's important for you to keep all these notes and numbers in your desk in case you need to refer back to them. You have them handy. I can guarantee you, if you keep your books and you keep your notes, you're gonna use them in the future. So that's a very important thing to remember. So again, once you get to your professional career, you're gonna make reference to all the things you learn in school. So make sure that you keep these notes and the things that you're learning in your degree. So that being said, now we're gonna talk a little bit more about other type of rooms, and this is a different type of room. These are called clean rooms. And if you have gone, I don't know if you have visited the first floor of this building, we have a clean room facility for the university. And the important thing about this is facilities planners are often called upon to design carefully controlled environments for electronics, pharmaceuticals, and for food processing operations. So these control environments are known as clean rooms. These clean rooms are very expensive. So the fact that we have one in our university makes us different. There's not a lot of universities that have these type of facilities. If you work for a pharmaceutical industry such as Johnson & Johnson, you'll see these clean rooms in most of the facility. And one way to distinguish them is that they're going to be painted with very clear colors, white colors, so you can see if there's any mold formation. And most of the people working in these rooms will be wearing these white covers throughout their body. So these are very important type of rooms. One widely recognized method used to achieve these air quality levels is the use of the HEPA, high efficiency particular air filters. And here I have a picture of the clean room that we have in this building. Um, so these filters are used in a wide variety of industrial, commercial, and institutional installations where the highest possible degree of air cleaning is required. So air quality is very important. So you need to have a way to keep the facility within a temperature, also move the air from outside to the inside and the odors outside the facility. So now we're going to talk about the HVAC design. So the purpose of this type of system is the heating, ventilation, and air conditioner is to control the temperature, the humidity, and the cleanness of the environment within a facility. The input required by an HVAC expert to design an HVAC system includes the facility layout, and the construction specifications. So the facility layout, again, there are going to be some departments that are going to require certain levels of humidity, certain levels of temperature. There will be some areas of the facility that will require different type of temperature and humidity levels. So you need to have a good layout plan for your facility in order to design the HVAC system. And the construction specification also tells the HVAC expert where the sun is going to hit the facility, so they can plan where to put the ducts and where to put the sensors to turn on and turn off the system and so on. So the facilities planning should be able to provide the HVAC expert with this input. Understand how the HVAC expert translate this input into the HVAC requirements. And here we have a picture of typical HVAC system. You can find this type of system in any house here in Texas. So you're going to have some type of compressor outside the structure, and then you have some ducts, heater system. Most of the time it's located in the attic of the house, and so on. So in terms of designing, the heating requirements for a facility is referred to as the heat loss, and is calculated using this equation. So we're going to have 7 different types of heat loss in your facility. So we're going to add them in order to get the total for the facility. So we're going to have the total heat loss through the floor, heat loss through the roof, heat loss through the glass windows, through the doors, walls, and due to infiltration. So each one of them can be calculated using this expression. So essentially what you have is the area of the facility component. So if you're dealing with the roof, we need to know the area of the roof. If you're dealing with the windows, we need to know the area of the windows and how many windows are we going to have, and so on. And we have a coefficient of transmission of the facility component, and most of the time this is given. And as I mentioned, this is the difference between the temperature, so the temperature inside the facility and the temperature outside the facility. So here we have, in terms of the air conditioning requirement for a facility, it's a little bit more complex because we have to take into account other things within the facility. So now we have 1, 2, 3, 4, 9 components. The floor, the roof, the glass windows, the door, the walls, the ventilation. Now we have to take into account the solar radiation, also the cooling load due to the lighting of the facility, and also we need to take into account the personnel. So we have same type of equation for QF, QR, QG, QD, and QW, and QD up to here. But to compute the QS, which is the one due to solar, we have these two components. Actually, this one right here, and then for QL, we have these equation, and for QRL, we have, for the lighting, we have another expression. So what we're going to do next is we're going to start working with these two things. But before we get to that, the cooling load from personnel may be calculated by determining QP, which is the number of men and women performing light and heavy work, and multiplying that times the heat gain factors given this table. So we can have heat gains. We have these four measurements that we can use depending on the type of employee that we have. So for a man doing a light work, we have 800 BTU hours. For a woman doing heavy work, we have 1,300. So now you see why you need to take physics when you get to this level. So we're seeing some of those ideas apply. So let's talk about this, or discuss this example. So we have a 18 feet tall facility having the dimensions of 250 times 100 feet, and the height 4 feet times 8 double pane glass windows, and 2 3x8 glass top doors on both the front and the back sides of the facility. The facility is made of 8-inch solid cylinder blocks and 1-inch metal insulated roof with an insulation seating and an insulated slab floor. The facility is located in Chicago, Illinois, so we want to compute what is the heat loss. And in order to get this, again, we need some data from the location or the area where this facility is located. So we have some of the factors already provided in the problem for each one of the Q's that we need to compute. And we also need to know what is the difference in temperature. So Ti is going to be 70 and T0 is 0. So we're going to be using these expressions here. We're dealing with the heating factor, so we're going to use these equations in order to compute the total heat loss for our facility. So again, the most important part, or the most difficult part here in order to get each one of these factors, is to determine what is the area that corresponds to that specific factor. So we can look at the first one. So let's compute QF. So QF is the heat loss through the floor. So we need to determine the area of the floor to compute this loss. So again, this is the equation that we are going to use. So Q equals the area times UF times T1 minus T0. So the area for the floor is given by this. So it's 250 times 100. So this is equal to 2,500 or 25,000 feet square times the U factor for that heat loss. So that's 0.81 BTU hour feet square Fahrenheit times 70 minus 0 Fahrenheit, which is the temperature difference in this particular area of sky. And then by multiplying those numbers, we get QF equals 14.175 times 10 to the 5 BTU hour. Questions? Okay, so one more time, the factors are provided for each one of the elements that we are considering for this heat loss. But the important thing is to determine what is the area that is going to constitute for the facility. What's the area that we need to take into account for that specific component? So let's look at QR. So QR is the heat loss through the roof. So what will be the area that we need to consider for this one? Say that again? Correct. So it's going to be the same area of the floor. Okay. Now that dimension is provided by the facility here, 250 times 100. So we're going to have the same area. So this is going to be 25 feet square times 0.2 hour feet square Fahrenheit. Zero 0.95 times 10 to the 5 BTU hour. Okay, so next we have QG. And QG is cooling load due to the glass windows. So let's see how many windows we have. We have 8. 4 times 8 double plane windows, and that's it. So this is actually telling you that you're going to have a double pane type of window. So each window will count as 2. So we're going to have 16 glass component with an area of 4 times 8, which is 32 feet square, times 0.63 BTU feet square Fahrenheit, times 70 minus 0. And that is equal to 0.06 times 10 square BTU hour. So the next component is UD, which is the heat loss through doors. And you're gonna work on that one individually, and you're gonna submit that. You can just use a piece of paper. If you don't have a piece of paper, I can provide you with some paper. The glass doors, they're single. Yeah. Anyone need paper? You have to complete the next one, which is the for the doors, UD. And this is going to be your lab for today. And UD is for the doors. So now we are taking into account the area of the doors. Make sure that you account for the number of doors. So there's 2 3x8 glass doors on both the front and the back side. So that means that you have 4 doors. What is the attendance sheet? Yeah. Anyone missing? Okay, so let me give you a hand here. So you have QD. We have the area times the factor times the difference in temperature. So we have the factor 1.13 BTU. Our feet square Fahrenheit times difference in temperature, which is 70 Fahrenheit. So the only thing you have to compute now is the area, and then compute the final number. Give you 1 more minute. Don't forget to put your name. Okay, so time's up. Anyone else? Okay. Yeah, there's a typo here, and thank you for letting me know. This number is not. This should be 0.226 and to the Okay, so going back to the problem, this should be equal to 4 times 24, and QD equals 0.076 times 10 to the 5 BTU an hour. The next one is a little bit more complicated. It's QW. So this one is lost through the walls. So we need to find the area of the walls, and we need to subtract the area of the windows in order to get the right area. So for that we have 2 times 4,500 feet square plus 2 times 1,800 feet square minus 16 times 32 feet square minus 4 times 24 feet square, all these times 0.39 BTU divided by hours feet square Fahrenheit, and then times 70. And that will be equal to 0.88 times 10 to the 5 BTU an hour. And I believe this is just for keeping them in the same boundary, but if you want to keep the large numbers, that doesn't make a difference. So we have QW we have one more component, which is QI, and that one is for the infiltration. So we're gonna have the area of the floor plus the area of the walls and then all these multiplied times 0.2 BTU hour feet square Fahrenheit times 70, and that equals 0.526 BTU an hour. And then finally we can get the heat loss by adding QF plus QR plus QD plus QW plus QI and that's going to be equal to 21.777 times to the 5 BTU an hour. And that's the last thing we're going to do today. Next, on Wednesday, we're going to look at the cooling. So this was for heating. We're going to look at the cooling on Wednesday. And we're going to cover the last two systems, the lighting and the safety systems, also on Wednesday. So remember to pick up your homework, which is here, homework 2 and 3. And I'll see you on Wednesday.
What is TW? Or what is it?
TW, that's
you.
for the walls. Yeah, so you find the area for the walls, and you need to subtract the area of the windows.
I accidentally made my UD 1.3 instead of 1.13 because I couldn't see from the back. Because right if I measure it real quick.
That's okay. Don't
You're
worry
not
about
gonna
it.
hit
Yeah,
it.
I'm
Okay.
gonna look at the expression. Okay.
Thanks.
Sure.